They say all good things must come to an end. Our life, until maybe people figure that out. We know a lot about aging. A star's life, just big old gas cloud. But the amazing story here, right? You know the cycles. They all start on the main sequence. More mass, they're gonna fuse stronger, right? More luminous, hotter over here, cooler. We have these three groups here. We've got low mass stars, including sun, that live a longer life because they're not as much gravity, slower fusion. High mass stars have shorter lives because they've got a faster fusion, more gravity, right? More gas, more mass, more gravity, faster fusion, and then very high mass stars. So these, of course, start as main sequence stars, either the G, the K, the M stars. They're cooler stars when they start. These, of course, start hotter as main sequence A and F stars. And again, the line is a little fuzzy, so you might see some variation in that call and that color. And these start even hotter as main sequence O and B. O, B, A, fine girl, kiss me, or guy, your choice there, right? So, and they go through those cycles. But there's a limit to how much gravity, how much these can squeeze. I mean, they do well, right? But these only get up to, I'm not going to do it this time. Okay, there you go. They only get up. They only can fuse up to carbon, which is 6 protons, and oxygen, 8 protons. And then they can't fuse anymore. So that's so our carbon, but even these will form this. So there's going to be a lot of carbon and oxygen, right, when these things blow. And there's this, and then they come back together. A lot of carbon and oxygen. Let's take a look. You can look this up. Easy search. Google search. Let's see, low mass stars. What do they fuse up to? Their fusion cycles. Let's see if I can do, there we go, much better. Right? Interesting. But then they just don't have the mass, the gravity, to go further. And as I said, these different shells can be fusing at different times. But then they're done. They're done. And let's see how they die in a moment. Now the larger ones can keep squeezing. The high mass and the very high mass squeeze. You got, what's that SI stand for? I'll give you a hint. Look that up. Just say SI. What is that? I'll give you a hint. Rocks. Think rocks. Oxygen. Neon. Carbon. Helium. Hydrogen. Iron. So squeezing these things together. And the story of, I'll leave it at that. All right. So what have we got here? What happens when they can't fuse anymore? Well, what happens to the low mass stars is that they go through this cycle. So we collapse and expand and collapse, and it's really kind of a gentle death in a way. I mean, they puff off this gas. They puff off this gas. And the ultraviolet, I should use purple, but my purple's fading, but the UV light of the leftover, it's still very hot, but there's a leftover, we'll talk about that in a second, illuminates and makes that gas glow. And just please Google images or internet search images of planetary nebula. They're gorgeous. And you can colorize. I realize you can colorize it so that you can see cool patterns like eyes and Eskimos and whatever, but it looks really cool. So that's happening in this fairly gentle death of a low mass star, but still, right, when they go through that red giant phase, Earth's going to have a hard time, isn't it? It's going to expand way out. You can look that up. So that's what that's. Now, these guys get up to iron, 26 protons. And when they're done, they go through a supernova explosion, a blast. We say N, SN, you'll see SN, that means supernova. They just can't fuse anymore. And that is a blast, right? You can look up the Crab Nebula or other, and we like to find them. There's a ton of information in that. So if I go over here again, let's just take, you can look at this all over public domain. What happens depends on the size of the star. So a small star, red giant. Oh, hello. Thank you for doing that. Supergiant. So, here's an example, but you'll see other ones. Supernova or planetary nebula, very cool. And what's left over? Oh, this leaves at the center a white dwarf. This leaves, neutron star and a black hole. I'll show you a little more clearly. Let's see what I've got in here. There's another way. Low to average mass, large mass, very large mass, another way to say it. And what do they leave? They leave those as corpses. Let me talk about those corpses a little bit. And then tell you that we've got a problem. And this is in the book, right? Let's go here. So the corpse here of a low mass star is going to be a white, which is hot, very hot, right? Dwarf, Earth size. Just think of sun. 100 Earths across, leaving one of them. The other gas has been puffed off, right? But it's so hot, creating ultraviolet, making that glow. It's a carbon and oxygen ball. Is it a diamond? Explore that. It's going to cool, and it'll just fade away. It's no longer a star. People sometimes call it a white dwarf star. It's like, no, it's dead, right? It's a white dwarf. The corpse. Oh, let me just say this. Yeah, you've got that. So how dense would it be packed in? Well, if you take a car and you squeeze it down and pack it into the tip of your pinky, sort of a thimble, right? The tip of your pinky right there, then that's a white dwarf. So try to pick up a car that's that size. You go to pick something up and you go, wow. Now the high mass stars will leave behind a neutron star. And there's a lot to say about that, but again, it gets a little overwhelming. I want to make sure that you retain this, but they really are crazy, and you can explore. They're spinning it in crazy rates. The physics of that, turning all into neutrons, is just crazy. And that's as dense as packing 3 times all humans on Earth into your pinky tip. And of course, there are fewer and fewer of these higher and higher, right? Up to 6 foot, and 6 to 7, 7 to 8, that idea. And this supernova blast, the corpse is a black hole. That's where a black hole comes from. There's 2 ways that black holes come. Okay, we'll talk about that in a sec. And that's like taking all of Earth, and packing it into your pinky. That doesn't even make sense, but it doesn't stop. It doesn't stop. Is there mass? That's what you say is mass. I mean, it gets funny. Words get funny. People say things. In fact, it just keeps going. What is it? Maybe the best explanation is it's a rip in space-time. Wait a minute. Okay, so low mass, fine. Maybe it leaves a diamond. High mass, these weird neutron stars, pulsars, things that are crazy. And a black hole where all the mass seems to go away. And there's a point at which, our theories work well, but we wonder. Oh, wait a minute. We wonder too about the start of everything, the universe, from out of nothing. No atoms. There was no explosion. There's no atoms. There's no chemistry going on. Just space-time expansion that turned into atoms and light, and the building blocks of atoms and light. So out of nothing comes something. And out of something goes nothing. There's something very interesting about space-time. Remember I said chapter 0, all space and all time? All matter and all light? Dark matter, dark energy, what is it? You can also get what are called supermassive black holes at the centers of galaxies. And I think I'll just leave that. You could have 4 million suns worth of mass disappear. It doesn't affect us way out here. It's just equivalent with 4 million suns, the pull. But there's a lot of other stars here, and they're pulling us. So turns out, too, that you can go into a supermassive black hole, and the tidal effect won't rip you to shreds. But if you go into a black hole, the tidal effect, the pull on one side of you versus the other, will rip you into shreds. The term that was given, I love the humor here, is spaghettification. So in some ways, the high mass star at the centers of galaxies is, the supermassive black hole, the centers of galaxies is a little more gentle. Now you're at the place where you can explore, right? I hope you have a sense of this universe. Time scales, it's crazy. It's crazy. The magnitude is beyond. We're tiny. These things are crazy. But wait a minute. But we came from, right? Before, as the universe expanded and cooled, you just had hydrogen and helium, a little bit of whatever. There's no carbon, there's not. And then they had to come together into the galaxies. And within the galaxy, you had from stars, and maybe the stars formed outside the galaxies. Explore. But most of the stars were low mass stars, right? But they'll get you up to carbon and oxygen. But these other ones will get you up to iron. Wait a minute, I've got a problem here. Okay, we're stardust, that's cool. But what about my jewelry? I've got a couple problems. These only build up to iron with 26 protons. Who's going to squeeze together the extra 3 protons to make your copper wire? Your silver with 47, that's protons. Gold with 79 protons. Uranium, the biggest naturally occurring atom, of 92 protons. If the 8-footer or the high mass stars can't do it, and there seems to be maybe a limit on how big a star can be, maybe up to 200 suns worth of gas and mass. So where do these come from? And the answer is, when you stop fusing, it collapses. As the gas in here collapses, the interior gas collapses. This iron, right, this whatever here, the interior gas collapses, rushes in, bounces back, and while that's bouncing back, the outer gas is rushing in, creating a shock wave so intense that the other bigger atoms are formed. When you have a piece of gold, silver, copper even, you should be realizing you're getting quite a deal. Look how cheap that stuff is. Heck, this gold ring, it was, when you give it to somebody, you go, hey, here's a ring that was formed, the atoms were formed in the shockwave of a supernova, and I give this to you. Because all gold was. It wasn't made on Earth. Well, you can do experiments, but you can't make enough of it to make it worthwhile. Gold, silver, the larger atoms were formed in the shock wave of a supernova blast. That's pretty cool. Come on. Our atoms were formed in stars, blasted out, and then, death isn't final, right? Our great-grandparents die. Our ancestors that looked up and told these stories that we're now tied much more closely to because they were tied to Earth and observing these things. When stars blow in some little region of the galaxy, the gas goes out and it compresses other gas. So there's gas out here, and then it squeezes gas, and that can generate new star formation. And around new stars can be new planets. And around new planets could be life. We certainly came. I mean, our Milky Way galaxy started more than 13 billion years ago. Our star didn't come into existence till 4.6 billion years ago. I think 5, whatever. So that'd be like 8 billion years, 8 or 9 billion years until, with our galaxy, all that stuff happening until our solar system formed. I mean, 4.6 billion is crazy to even conceptualize. But to realize that our atoms were formed in, remember, a big mama or a bunch of big mamas that exploded. They fused this stuff, exploded, leaving these things around. That's pretty cool. And we get bigger and bigger telescope, and we keep exploring, and some of you may want to go into that. And you can work on it in anything. Computer scientists, electrical engineers work on this stuff, mechanical engineers a lot, and physicists, of course, and astronomers and so on. So it's a great journey, but if you do that, you're not doing something else. We enjoy the musicians, because this is a human journey, just like the history of art and the history of music and the history of politics, right? The history of sport. Go back to the Olympics, go to other cultures, right? But we found out, right? The history of humans. This is all part of it. Who knows where we'll go? But I just want to say, it's overwhelming. But you don't have to change the world, we just do our part. Someone that's waiting at a table at a restaurant, I'm so grateful if they're nice. Right? They're good. I'm grateful for whatever people do. We contribute, and hopefully, we play a little guitar and we enjoy. And so, in the end of it all, this is the story of the universe. And it's also the story of our exploration and discovery of the universe. And when you try to tell this to a friend and 5 minutes are hanging out, it's a little overwhelming. You realize how much you've learned, and you sit out under a night sky and you think of these nuclear fusion factories that are going through cycles and that will blow and leave this stuff. Most of them here, some of them there. And we just keep looking and exploring, building better technology, better medical technology, better fun technology, and all that. So I hope you enjoy that. Chapter 12 is a short chapter on cosmology and galaxies, which your class may or may not, my class may or may not get to, but I think it's pretty fun too. Short, and so you could enjoy that. But particularly, there's so much information out there, and I think it's hard to get this framework to see these connections. And I hope I've helped you to get this context and framework so that you can go further or dabble in, just as a lot of us dabble in music, or we dabble in cooking, or we dabble in whatever. So dabble away, contribute, create, enjoy, eat pasta. Cheers to you, and cheers to us. Stardust.